students. So in the previous lecture we have discussed about the Hoffman's exhaustive methylation followed by the isolation of conine of nicotine. Isolation of this conine. Isolation of a conine we have discussed. Just I will brief out what we have discussed in the previous period, that is Hoffman's exhaustive methylation. As I told, is a very important process in the heterocyclic ring system. So here what happens, first the uh, heterocyclic ring system is ring is opened with the elimination of a nitrogen. Heterocyclic ring is opened with the elimination of a nitrogen, so that we are going to get here a carbon skeleton. So knowing the carbon skeleton, we can find out the structure of that particular heterocyclic ring system. Okay, so there is a simple procedure here. So alkaloid, that means, or a heterocyclic ring system. So if it is unsaturated, so you go for the reduction. You reduce it so that you are going to get a saturated heterocyclic ring system. So that should be subject. That means that should be converted into a quaternary methyl ammonium hydroxide. Quaternary methyl ammonium hydroxide by treatment with the methyl iodide followed by the silver hydroxide. Okay, so it will be converted into quaternary methyl ammonium hydroxide. In the next step, it should be heated. So when you heat it, so there will be an elimination of a water molecule. So when the water molecule is eliminated from the heterocyclic ring system, so ring is opened at one side of this heterocyclic ring system. Okay, then again you have to repeat the process. That means you treat it with the methyl iodide followed by the treatment with a silver hydroxide. So we are going to get again the quaternary methyl ammonium hydroxide, which on further heating, so that another water molecule is eliminated and the ring is opened at the other side of the heterocyclic ring system with the elimination of nitrogen. So nitrogen has been completely eliminated from the heterocyclic ring system, and you are going to get what? You are going to get a carbon skeleton. So knowing this carbon skeleton, we can guess the structure of this heterocyclic ring system. So to find out, to determine the structure of this heterocyclic ring system, so this Hoffman's exhaustive methylation is used. So it's a very important process, and as I already told you that it has been asked number of times in the previous annual examinations. Okay, then we have also completed, that means studied the isolation of this conine alkaloid. So this conine, as I already told, is a highly poisonous alkaloid. So which should be isolated from the hemlock harum. So to isolate this, what we have to do here, the hemlock herb seeds are to be collected and they should be dried and they should be powdered. To make it powder of these seeds of hemlock herb, and then that powder is to be subjected for the distillation with sodium hydroxide. You distill with the sodium hydroxide, so that what happens, you collect the distillate, and then that distillate is subjected for the ether extraction. You go for the ether extraction of that distillate. So you collect only the ether layer. And then that ether layer should be subjected for the evaporation of ether. Evaporate the ether, so that you are going to get a residue. So that residue contains the impure conine. That impure conine. Further, to get the pure conine, what you have to do, you subject that one for the fractional distillation. And the residue, which is to be collected at 166 degrees Celsius. So you are going to get this conine. Pure conine is to be collected at 166 degrees Celsius by subjecting it for this fractional distillation. So you are going to get a pure form of this conine. So conine is isolated from this hemlock herb. So this may be asked for 2 marks. So how this conine is to be isolated? Give the isolation of conine for 2 marks. Okay, so this is what up to this we have discussed. Now the next part is a very important part, that is we are going to discuss the constitution of a conine, or structure of this conine. How the structure of the conine is to be evaluated. So for that, what we have to do, so we have already got the pure form of this conine. Pure form of the coninine we have isolated from what? Hemlock herb. Okay, so that pure form you take it and first you subject that coninine for the elemental analysis. Elemental analysis. Elemental analysis means what we have to do? First you subject that coninine for the elemental analysis. Elemental analysis means which elements are present in that coninine. Okay, so knowing that you go for next estimation of elements. Estimation of elements. Estimation of elements means so that means by estimation of elements we are going to know the percentage of each element present in that coninine. Yeah, that is percentage of each element present in the coninine we are going to know. Okay, and the molecular weight is to be determined by this mass spectroscopy. Directly we will get the molecular weight from this mass spectroscopy. So knowing this mass of this coninine, so we can first calculate the empirical formula, and then we are going to calculate the molecular formula. So by doing all this elemental analysis and molecular weight determination, the molecular formula of this coninine is found to be, so it is a C8H17 and N. C8H17 and N will get. Okay. Now to get the structure, so we have to carry out some chemical reactions also. Okay. So you take this coninine. Okay, so which has the molecular formula of C8H17 and N. C8H17N. So this should be subjected for zinc dust distillation. Okay, we subject it for zinc dust distillation. So when you subject for the zinc dust distillation, so you are going to get one more compound which is called as a conirine. You get the conirine on subjecting this coninine for the zinc dust distillation, and the molecular formula of this conirine is also to be determined. That comes to be, it is a C8H11 and N. C8H11 and N. So whatever the product we got here by the distillation of this conirine, zinc dust, conirine which we got, so its molecular formula is going to be C8H11N. Then what is the difference between this and this? So there are 6 hydrogen atoms are less. That means there is the elimination of here 6 hydrogens from this coninine. 6 hydrogen atoms have been eliminated, removed from this coninine to give this conirine. Now further, this conirine is subjected from the oxidation with the potassium permanganate, KMnO4. Then subject for the oxidation with potassium permanganate. So you are will get a known compound that is nothing but a pyridine 2 carboxylic acid. So it is nothing but a pyridine 2 carboxylic acid. Pyridine 2 carboxylic acid, known compound we will get. So already you know this is a pyridine. This nucleus is pyridine. So at the second position there is a carboxylic group. So it is a pyridine 2 carboxylic acid, or it is also called as a picolinic acid. Picolinic acid we will get here. Okay, so known compound we will get. So as we have got this pyridine 2 carboxylic acid formation indicates that definitely this conirine also contains this pyridine nucleus with a side chain at the second position, because in the process of oxidation the ring will not open. Only the side chain is going to be oxidized. So as we are getting here the pyridine nucleus, definitely this conirine also contains the pyridine nucleus with a side chain at a second position. Okay, so this means the structure of this conirine. We don't know the side chain. Leave about side chain. So conirine may have this nucleus. It must have a nucleus of this pyridine with the side chain at a second position. Then what about this now? Now here there are 6 hydrogen atoms are less, because in the process of this zinc dust distillation 6 hydrogen atoms have been removed from this. That means when you add 6 hydrogen, means these 3 double bonds are to be reduced. 3 double bonds are reduced. So you are going to get a nucleus. What we already know that is a pi pyridine nucleus. So this is nothing but a pi pyridine, because you add these 6 hydrogen atoms. 6 hydrogen atoms, so it should be reduced and you are going to get this nucleus. So this is the pi pyridine nucleus with the side chain at second position. That means from this reaction we come to know that this conine it is containing this pi pyridine nucleus with the side chain at a second position. So you follow now. So this conine is containing pi pyridine nucleus with the side chain at the second position. Okay. So this nucleus is there. Then we have to find out what is this side chain. What is the side chain? So you know already the this molecular formula of the conine. So what we know the molecular formula of sorry, we just write conine. Conine. So conine molecular formula is C8H79N. H79N. Then what is the molecular formula of this pi pyridine nucleus? Pi pyridine nucleus. So see 1, 2, 3, 4, 5. So there are 5 carbon atoms. 5 carbon atoms. And how many hydrogens? 2, 2, 2, 2, 8 hydrogens. And here 9 and is a 10. So 10 hydrogens and 1 nitrogen atom. Nitrogen atom. So this is the molecular formula of this pi pyridine nucleus with the side chain at second position. So this is the molecular formula. Then when you subtract this from this, you will get this side chain molecular formula. You subtract this molecular formula from this conine molecular formula. So what we will get? So 8 hydrogen atoms, 8 carbon atoms are there. Here there are 5 carbon atoms. So you are going to get here 3 C3. Hydrogens here 17 are there, here 10 are there. That means it is a 7 hydrogens. 7 hydrogens. Nitrogen is there, nitrogen, no, cancel. So the side chain is C3H7. C3H7. So here if you write this C3H7 here, side chain C3H7. So this may be the structure of the conine. This is the structure of this, and this coincides with this molecular formula. That is C8H17N. Okay, then we will find out what is this C3H7. What is the structure of this C3H7? So C3H7 can be written in only 2 ways. So we write in straight chain, then CH2, CH2, CH3. This is one thing. This is N propyl group. You know this is the N propyl group. Or this can also be written in another form, that is the iso form. Isopropyl group. You can write it in the isopropyl group. So this is a N-propyl group, or this is a isopropyl group. So here you can see 3 carbon atoms, 4, 5, 6, 7. That means C3H7. Here also 1, 2, 3 carbon atoms. Here 6 carbon atoms, 7 carbon atoms. C3H7. So the C3H7 can be written only in these 2 ways. So if you write the structure of this conine with the side chain at second position, so we can write like 2 structures we can write. So this is, we can call the structure 1, and this with the side chain of this, the normal side chain, normal N propyl group, and another structure we can write where there will be an isopropyl group. There will be here H will be there, here H is there. So it is a CH3 and it is a SCH3. So this is the second structure. So we will get 2 structures for this conine. Conine can be written in 2 structures. Now whether structure 1 is correct or structure 2 is correct. So that we have to find out. So for that what we do, we use some of the reactions here. Okay. So the structure 1 is correct or structure 2 is correct. So for that what we do here is the conine is subjected for the heating with the hydroiodic acid at 300 degrees Celsius under pressure. What you do, you heat this conine with the hydroiodic acid at 300 degrees Celsius under the pressure, so that you are going to get a normal octane. You will get normal octane means CH3, CH2, CH2, CH2. Okay, 1, 2, 3, 4, 5, 6, 7, and it is 8. Oct means 8. There are 8 carbon atoms in the ring sustain. Okay, so this is nothing but a N octane. N octane is to be octane. Then octane is to be obtained when the quinine is subjected for heating with the hydrochloric acid at 300 degrees Celsius under pressure. So you are going to get this. That means what you got here is you have got a straight chain. You got the straight chain here. There is no branching. So definitely this structure is correct because here you are getting a straight chain. Here is the branching is there. Branching is there. So if you could have here, so you could have got isoctane, you could have got isoctane, you could have, but you are getting here this normal octane, which indicates that the structure 1 is correct. Structure 1 is correct. Okay. Then also another evidence for this is we go for the to confirm the structure 1. So we have to go for again the Hofmann's exhaustive methylation. It's a Hofmann's exhaustive methylation which we have already discussed. Hofmann's exhaustive methylation. In that, you take the structure 1 and we confirm. Okay. Start with the structure 1. CH2, CH2, and it's the SES3. Okay, this is the structure 1 which we have confirmed, and further we are going confirming by this reaction. Okay, then you take this and treat it with the methyl iodide first. We will go step by step. Okay, so as I already explained, this nitrogen atom having the extra lone pair of an electron, and here due to the minus I effect, this is rich in electron, this is deficient electron. So a nitrogen is going to attack the carbon atom, so that you are going to get here the methyl group is going to attach to this, and there will be a positive charge here, and you are going to get the iodide ions. Okay, iodide ions. Okay, further when you carry out here another molecule, so this is to be eliminated, and that the hydrogen is going to be replaced by the methyl group. Methyl group. Okay, we will get plus charge here, and this iodide ion we will get. Okay, this is a quaternary ammonium iodide you are going to get. Quaternary methyl ammonium iodide you will get. Then this should be treated with the silver hydroxide. Silver hydroxide, so that the silver has a greater affinity to the iodide. So the iodide ions are replaced by the hydroxide ions. So that what you will get here? So methyl plus charge. And here OH minus ions you are going to get. So you are going to get what? Quaternary methyl ammonium hydroxide, what I have told. So that first it should be converted. Heterocyclic rings is to be converted into quaternary methyl ammonium hydroxide. Then this should be heated now. Just to heat it so that there will be elimination of the water molecule. See, here is the hydrogen at the beta position. So we use electrons, so that nitrogen takes electron, that means this bond is to be broken. H will come out in the H plus proton. So this proton and this OH minus water molecule is eliminated, so that this bond is going to be broken. So you are going to get this like this. Okay, structure, there is a 2 methyl groups here. Okay, methyl group, you get double bond, and the water molecule is to be eliminated. Okay, this you will get. Now further you repeat the process. There is a methylation and treatment with this silver hydroxide. So first you go for the methylation. Similarly, this nitrogen attacks here, and you are going to get a this hydrogen, methyl group attacks this nitrogen because this is a extra lone pair of electrons. So third methyl group here, there will be a positive charge, and there will be iodide ions. So you are going to get a quaternary methyl ammonium iodide you will get. So further it should be treated again with the silver hydroxide. Same steps. These same steps are going to be repeated here. So when you replace, that means here iodide ions are replaced by the hydroxide ions. Here is a double bond. Okay. Now you will get here again. Here is a CH3, here is a CH3, is a plus, and here is a OH minus. Okay, OH minus. That means quaternary methyl ammonium hydroxide. Methyl hydroxide you are going to get. Further it should be heated. Same step. So here the beta hydrogen from the other side of the mixer state. So here B, nitrogen takes electrons, again this is broken, this comes out as the H plus, okay, this H plus and this OH minus, water is going to be eliminated, so that the ring other side is to be open, other side of the ring system is going to be open. So you are going to get here double bond here, double bond here, this nitrogen has been eliminated, so you will get this. So this further, so this should be isomerizes, so that it is unstable, so this bond is to be shifted here, so you are going to get this is a product we will get, which we call it as a conylene. It's called as a conylene you are going to get. A conylene you are going to get. This conylene further you subject it for the oxidation, so reduction. If you reduce this, so what we get 1, 2, 3, 4, 5. So you are going to get here n octane again. You will get n octane. Okay. So the formation of this conylene, which indicates that so there will be the ring should be like this. The ring, it means heterocyclic ring system should be like this. That means we confirm that there should be a ring system is like this. Okay, so this is how I think I have not written this good, sorry. So this group is to be written CH2, CH2, CH3. This I have not written. So every pair you can write this CH2, CH2, CH3. Okay, here also you should write CH2, CH2, CH3. That thing I have forgotten to write. So that here also you write CH2, CH2. That the side chain I have forgotten to write. So here also you will get CH2, CH2, CH3. Then only you will get this octane. Just as a reduction. That means these two double bonds are going to be reduced. So you are going to get a n octane. Here also you got n octane. Here also you got n octane. Here also you got n octane. So the such side chain should be a straight chain. It should be a straight chain and propyl group. So that the structure 1 here also it is confirmed. It's confirmed here also. Treatment with hydrochloric acid. In this reaction also we confirm the side chain should be a straight chain, is n propyl group. And here also in the Hoffman's exhaustive methylate also we confirm that the n octane which will straight chain. So here also we confirm that it is a n propyl group. So by these two reactions we have confirmed the structure 1 is correct for this conine. Now further again this conine is also confirmed by its synthesis. So synthesis also we can confirm the structure of this conine. So that is a synthesis of conine. Okay. So it's been synthesized from the starting material is alpha picoline. It's called as alpha picoline. Starting from the alpha picoline, we can easily synthesize this conine in the laboratory. So naturally we got it. Naturally we got it from the block herb. Correct? So we have isolate in laboratory also we can synthesize. And whatever this we have synthesized in laboratory and also what we got it from the hemlock herb, both are to be compared. Both are to be compared. So if it matches, then the structure is correct. Okay. So here what we do, you should treat it with a acetaldehyde, CS3CHO. You treat it with acetaldehyde here. This alpha picolinic acid should be treated with what? Acetaldehyde. So that what happens here? So just 3 hydrogens I will write like this. Okay, 3 hydrogens. Okay, then these 2 hydrogens and this oxygen, there will be elimination of water molecule. Hydrogens and oxygen, water molecule is to be eliminated. So water is to be eliminated so that this carbon is now linked to this carbon by the double bond. Okay, double bond. Okay, so what we get here now? This is okay. C. CH is left here. This is a CH. Okay, CH. Now double bond, CH, and this is a SCH. Okay, CH. We got this product. Then this product is subjected for the reduction. Just simply by reduction with the sodium and ethanol. Sodium and ethanol. So when sodium ethanol is treated with the sodium, hydrogen is to be evolved. Hydrogen gas is to be evolved. That hydrogen gas is reduced. Now here is double bond. This double bond is also reduced. In these three double bonds are also reduced. Three double bonds. Here three double bonds. Here the fourth double bond. All the double bonds are reduced by the addition of hydrogen here. That means totally 8 hydrogens are required. 8 hydrogens are required here. Or 4 molecules of hydrogen also required. 4 molecules of hydrogen are required to reduce this product, so that when it is reduced, what you will get here now? Here one molecule of hydrogen is added to this double bond, here one molecule, here one molecule. That means here to this nitrogen, one hydrogen is to be added, and this double bond is also dismissed. One hydrogen added here, another hydrogen is going to be added here. That means CH2, CH2 and CH3. So you got this point. Cumene job synthesized only in 2 steps. In the laboratory, easily we can synthesize this cumene, and whatever this cumene synthesized in the laboratory and what the cumene which we got it from the hemlock herb, so both are to be compared. They should be analyzed, and the both are same, so the structure of this cumene is confirmed. So this is structure 1 which we have already got it is confirmed. So this is how the structure of this cumene is evaluated. This is called as a constitution of this cumene, or the is also called the structure of the cumene. So like this, so structure is to be confirmed. So in the examination they may ask, discuss the constitution of cumene. Discuss the constitution of cumene for the 5 marks. But sometimes they may also ask for 2 marks. Give the synthesis of cumene. Only for 2 marks. Give the synthesis of cumene. Okay. So this one alkaloid we have discussed. So its isolation and also its constitution with the synthesis. So we'll stop here. We'll continue in the next period. Okay.